talking about chapter 6, okay? And then since the time is very limited, so I will go pretty fast. So, and then on this Thursday, okay, it's possible to make up 1 hour class from the 1 o'clock p.m. 有没有办法？今天这个礼拜四，我们从1点开始上，补1节课。Is anyone has a problem from the 1 o'clock this Thursday？ 这个礼拜四，我们补1个小时的课。Okay, since next week we have holiday. Okay, next Thursday we have a lot of holiday this semester. Okay, anyway, so this Thursday, okay, we make up 1 hour class from 1 o'clock. Okay, and we can see. Anyway, so here is chapter 6 talking about the surface wave. Okay, and this is a physical problem we have. Okay, we have a surface with a wave, and we like to study how the flow field look like for this kind of surface wave. And as I mentioned before, okay, this surface wave we were using the potential flow to solve this physical problem. Remember, okay, potential flow instead of viscous flow, we don't consider viscosity effect. So on this interface here, we have interface here. On this interface here, we have to satisfy 2 boundary conditions. One is called the kinematic boundary condition. So first we define what the free surface look like. Free surface is defined as y is equal to a dot function of xzt. So we have to remember this on this free surface here. And how we define on this free surface here, on y equal to a dot. This a dot is function xzt and t. There is no y here. Y is here already. So this is our coordinate system. This is x, this is y, and this is maybe z. Okay. So this is a function of. So give me any point on this free surface can be represented by using a y equal to a dot. And y a dot will be function of xzt. Okay, as mentioned here. Okay, and what's the kinematic boundary condition? Kinematic boundary condition is like this. This is the kinematic boundary condition. It describes what? Describe the y equal to a dot. Y minus a dot is mean y equal to a dot equal to 0, right? Take a substantial derivative. Okay, and then what this physical meaning is when you have a fluid particle, any fluid particle here. Any fluid particle here, okay, if you're treating this fluid particle, it's always on the free surface. Okay, and how do we define the fluid particle? Fluid particle is y minus a dot, right? Y minus a dot. That's the fluid particle on the free surface. Okay, this is equal to 0. And then d dt is what? D dt is follow a substantial particle, right? Follow a fluid particle. This fluid particle didn't change with time on the free surface. Okay, and I can show you clearly to be able to understand. This is a fluid particle. Okay, this is a fluid particle. This fluid particle, even our surface wave is traveling. This fluid particle always stay on the surface. Okay, and this, as you can see, just moving like this is a circular motion of this fluid particle. Okay, but it's always on the free surface. Okay, so the physical meaning for this equation you should be able to understand. Any fluid particle, if you follow that fluid particle on the free surface, is okay. That is always on the fluid particle, always on the free surface. Okay, so this is d dt, and d dt represents the substantial derivative, as you remember. Okay, previous time. So how do you expand this substantial derivative? D dt become partial t, right, plus u dot gradient of this. That's a substantial derivative, right? And so we try to evaluate this. As you can see, y is a variable. So y partial t is equal to 0 because y is an independent variable. Okay, x, y, z, t is all independent. Can you follow me? So partial y partial t will equal to 0. Only the partial a dot partial t because a dot is function of t. And here, okay, as you can see, you have a u dot gradient, right? Y minus eta. And then, as you can see, if you extend that, okay, will be equal to what? U dot partial y minus eta partial x, right? Let me expand. So if you expand this, right? Then this will become partial t y minus eta, right? Okay, and equal to u partial x y minus eta plus v partial y minus eta, right? And plus w partial z y minus eta. Okay, and then as you can see, partial y partial t is equal to 0. Okay, this y and t are independent variables. So for this term here, we only have partial eta partial t minus sign here. And this u dot partial y partial x, y is in the y and x are independent variables. They are not. Okay, there is no relationship. Okay, so this one will be equal to 0. So here we have only plus u, okay, partial eta partial x. Right, this take minus sign here. Minus sign here partial eta, because the eta is partial x dt. And as you can see here, partial y is equal to 1. Eta is not function of y, so this is equal to v, right? This term here equal to v. And here we have a w plus w. W partial y partial z is equal to the, they are two independent variables. But eta is z function, so it's partial eta partial z. Okay? So the eventual equation will be simplified like this. Okay, so if you extend this, equation will be simplified, become like this. Okay? And then if you just change the, okay, partial u, partial eta, partial t plus u, we can change to partial phi, partial. This is velocity potential, and times partial eta, partial x. And plus w can be written as a partial phi, partial z. That's the velocity potential, right? And then times our partial eta, partial z. And our our v can be moved to the right hand side equation, and v is equal to partial phi, partial y. Okay, so that's this is another movie. Okay, fluid particle. Okay, on this interface, always on the interface, didn't change with time. Okay, that's the kinetic boundary condition. Okay, we should have on here, on this surface here. So we should have this relationship. The second relationship we should have is called a dynamic surface boundary condition. Okay, on the surface, okay, pressure should be equal to, should be satisfied to certain equation. And then since we're using the potential flow, right? Potential flow, any potential flow related to the pressure is a Bernoulli equation. So this is unsteady Bernoulli equation we have in the chapter 1. Okay? And so here we have a partial v, partial t. And since we are incompressible, so rho is a constant, for example. So if we integrate, become p over rho here. And this is the 1/2 gradient phi dot gradient phi here. And this is a gravitation force. Gravitation force is equal to g eta, because we have our coordinate system is like this. This is our y equal to 0. Okay, so this is height is eta. Okay, y equal to eta is the interface. So at the interface here, we have the gravitation is g eta. Okay, and this is g eta is like this, and equal to ft. So you can return this Bernoulli equation. Okay, like this, unsteady Bernoulli equation. Okay, so this is dynamic boundary condition. Any interface pressure should satisfy this equation. Okay, if I know the flow field, all this flow field, I know eta, all the flow field, I should be able to know the pressure on the free surface. So this pressure on the free surface is equal to P, capital P, when y is equal to eta. So this is satisfied on only y equal to eta. Okay, so it's on the interface. So we have a carbon equation for this physical problem. Look like, okay, since we are using the potential flow, so every flow is governed by Laplace equation. Laplace phi equal to 0. Okay, all the flow fields can be governed by this. And on this interface here, right, we have y equal to eta, and we have a so-called kinematic boundary condition. Okay, and you have this. And we have y equal to eta, again, is represented this interface here. We have a dynamic boundary condition. Okay, this is from the Bernoulli equation I just told you. Okay, so on this interface here, we have two boundary conditions. One is represent the kinematic boundary condition, the other is a dynamic boundary condition. And then finally, on the bottom wall here, bottom wall is a y equal to minus h, since this is h, so y equal to minus h, right? And on the bottom wall, we have the surface here, no flow across this boundary normally, right? That's a potential flow. So partial phi, partial y represent the y direction velocity. So partial phi, partial y should be equal to 0 at this boundary. On the bottom wall, y equal to minus h here. So if you return the Gaussian equation with the boundary condition completely for this physical problem, it should look like this. Okay, that should look like this. So if you solve this, okay, Laplace phi and satisfy this boundary condition, they can represent the flow field for this kind of flow. But for this, we can see it's very difficult to solve, right? Because we have all kind of the, okay, eta is unknown, right? And then Laplace phi, gradient phi times gradient phi, this is nonlinear term. Okay, nonlinear term will be difficult to interpret. Okay, so since for this physical problem, if we can linearize this equation, okay, under some assumption, we can simplify this physical problem. And the way to simplify this physical problem, we're using so-called small amplitude plane wave. Okay, what's a small amplitude mean? Okay, I will tell you what's the definition for small amplitude. The amplitude is very small. Okay, the wave, the amplitude is very small. And how small is called a small amplitude? That's the other. Okay, you have to know. So again, our Gaussian equation didn't change. Okay, this is our Gaussian equation, Laplace equation, equation. So since we assume this is small amplitude is eta is small. However, small is relative, right? You can eta is small. We have to say relative to what? Compare with what? Compare with the wavelength. Okay, so this is wavelength. So our reference scale with eta. Okay, this is our wave, right? This is our wave. And from here to here, we have here to here is one wave. This is lambda. This is wavelength. Okay, and eta is what? Eta is this. So eta should be much less than. Okay, that's a small amplitude assumption. Okay, this is eta is amplitude for this wave. So this eta amplitude is compared with this wavelength, which much smaller than this wavelength. And here we know this is the x direction, right? This is x direction. So as you can see, partial eta, partial x. This is slope, right? Slope is partial eta, partial x. Since x is a lambda direction, right? So this should be also small. Okay, very small. Okay, very small. Less than 0. Okay, so by using a small amplitude assumption, okay, eta is small compared with wavelength. So partial eta, partial x, which is the slope of the free surface, which will be also small. Okay. So if you're using this assumption, small amplitude assumption, apply to the boundary condition we have. This is a boundary condition so-called kinematic boundary condition we just introduced to you. This is this boundary condition. We call it kinematic boundary condition. You written down this. We copy this here. Okay. So partial eta, partial x is a small, right? This is small number. So this term can be dropped. This is u velocity, okay? And this is, we don't have any, since we assume it's a plane wave. Plane wave means we don't have any, with a 2D wave. 2D wave is not a function of z. So this term, any related to the partial z term will be dropped, okay? So we only have this partial v, partial t equal to partial v, partial y is this. Okay? As you can see here is also the problem, y equal to eta, right? We don't know where is eta for this physical problem right now, okay? So if we can simplify, since eta is very small, so for this equation here, we can also simplify. This is the equation we just write, and this is eta, right? And if you extend this by using the Taylor expansion, partial v partial y is x eta t, right? Eta is very small, okay? So we can written as partial v partial y as y equal to 0, right? This is y equal to plus eta partial square v partial y square s. So this is, everything is evaluated as y equal to 0, y equal to 0. So only eta here, since eta is very small, so this and this should be very close. So we can rewrite this eta here. Instead of using the eta, we're using the 0. Okay, to represent, simplify our physical problem because it's so close. Okay, small amplitude. So our kinetic boundary condition can be reduced this. Okay, this is original by using the partial eta partial. Okay, it's a very small number. Okay, and this is a plane wave. So we have this equal to this. However, we have eta here, and this eta can be changed to 0 because Taylor expansion tells us when eta is small, this term and this term is very close. Okay, so we have the boundary condition reduced to this, so the kinetic boundary condition. Okay, so that's under the small amplitude assumption. Okay, and then we linearize our kinetic boundary condition. This is linearized. After linearized, you can see we don't evaluate any. Okay, only evaluate y equal to the partial v partial y, and this value equal to partial eta partial t. Okay, and dynamic boundary condition. Okay, we also can linearize by using the similar. Okay, this is the original. Okay, dynamic boundary condition, and we already neglect because u is very small. Okay, as you can see. Okay, since our perturbation is our amplitude is small, our u velocity is very small. Okay, so this is u dot u is a small number times a small number. So gradient phi times gradient phi is also even smaller, can be neglected. Okay, so if you compare with the previous here, we have this term here, right? And this is very small, and this can be dropped. Okay, because our small amplitude assumption can give us this is also small number. So we have the rate of turn written as here. Okay, this is and also we can expand that. Okay, since this is eta, right? Y equal to eta, right? And we can also using the Taylor expansion. So partial v partial t, instead evaluate y equal to eta, we can evaluate y equal to 0 because when eta is very small, this and these two numbers very close, right? And we copy this and copy this, and so we can instead evaluate y equal to eta, we can evaluate y equal to 0. Okay, that's another due to the small amplitude assumption. As you remember, okay, phi is the velocity potential, and psi is a string function. Okay, there is no psi equal to a constant, just represent the equipotential line, right? And then this equipotential line equal to a constant, and there's no physical meaning. So for this constant here, we can add into this, okay, velocity potential. So this velocity potential plus this integration, if you integrate with the time, okay, give you the integration for this, okay, this constant. This constant can be added into the velocity potential. This can be represent a new velocity potential without any sacrifice, any physical meaning. Okay, we can change any phi. Okay, phi is to equal to only the different phi is equal to a constant. Is no physical meaning. Only represent one potential line. Okay. So if I add a constant, didn't make any change. So I just include this into our velocity potential. So this equation can be simplified as 0 here because ft is already absorbed into velocity potential here. Okay. So our linearized dynamic boundary condition can be written as like this. Okay, so after the linearization, okay, our boundary condition for this physical problem become like this. Okay, so here is a kind of a, okay, so we have the linearized dynamic boundary condition. This is the linearized dynamic boundary condition. Okay, okay, we can substitute this because we have a partial eta partial t here. And partial eta partial t will be equal to partial v partial y, right? So for this equation, dynamic boundary condition here, eta is here. So we take a derivative of this eta with respect to time. and everything is repeated. So this become partial square t, partial square phi, partial t squared, right? And this is become what? Partial p, partial t, okay? And this is g times partial a dot partial t. Partial a dot partial t can be represented as a partial v partial y. So this is partial v partial y here. So our dynamic boundary condition enclose our dynamic boundary into the dynamic boundary should be written like this. Okay. And another boundary condition on the bottom wall or on the bed here is unaffected because at partial v partial y equal to 0, right? At y equal to minus h, so this should be the same. So here is original. We have this carbon equation, dynamic boundary condition, okay? And then this is bottom wall boundary condition. This is two boundary condition on the interface, including the kinematic, dynamic. Okay, this is original equation. Under the small amplitude plane wave assumption, okay, we can simplify become like this, as you can see, okay, become two-dimensional part is xy function, and this equation can be simplified. This kinetic boundary condition and dynamic boundary condition will become like this, and our boundary condition on the bottom wall should be the same, okay. So that's it. After linearization, okay, this is a physical problem we will deal with under the small amplitude assumption. A small amplitude plane wave assumption. Okay. Okay. Once you have this, we start to can solve the problem. Okay. We can start have a physical problem. So first, we specify okay a small amplitude on the top on the interface. This is a dot function. Y equal to a dot is represent this interface, right? So when we have the interface is a sinusoidal function. Is a epsilon is a small amplitude, okay? It's a sine 2 pi over lambda x minus ct. So this is x, this is y, okay? And for this interface here, can be written as a dot is written by this function here. Okay. Once we have this interface, okay, sinusoidal interface, what the flow field look like underneath here? Okay. So we give me the boundary condition. This is boundary condition we have. Okay, give me the interface equation, and I can solve the flow field underneath for you. Okay, by apply this, by solving this equation under this interface bound, okay, condition. Okay, this interface equation, I can solve the flow field. Okay, and here we assume, okay, our pressure is a constant. So this is for this pressure here. This is a carbon equation. This is the three boundary condition. Okay. So the pressure here is not functional type because outside we assume this is all atmosphere pressure. Okay, so this interface outside here, this is liquid, this is air, and outside the interface here, without only consider the surface tension yet. Okay, if you consider surface tension later, okay, but right now we don't consider surface tension. And when you don't consider surface tension, pressure above is all atmosphere pressure. So this atmosphere pressure is a constant everywhere. Okay, without any consider the surface tension. So this partial P, partial T will be neglected because the P is not functional time, it's a constant. Okay, so we can rewrite our carbon equation and boundary condition. The carbon equation should be the same, right? And this boundary condition will be because the partial A dot partial T here, and A dot is already this function. So we take a time derivative, right? And this time derivative become 2 pi c, right, and take a minus sign. So minus epsilon 2 pi c over lambda. Sine become cosine, right? Sine become cosine 2 pi over lambda x minus ct. So this is okay, the boundary condition after using this interface equation into this boundary condition should be look like this. Okay. And the dynamic boundary condition here, okay, partial square phi partial t square should be the same. And this is g partial p partial y should be the same. Only I neglect the p is a constant, so this term drop. The bottom wall boundary condition will be the same. So this is a physical problem we should solve. Okay, under this sinusoidal surface wave. Okay, we have a sinusoidal wave surface wave, and our flow field should be governed by this. Okay, boundary this carbon equation with these three boundary conditions. Okay. And then how to solve this? Okay, as you can see, we can solve this by using separation of variable. And how do we guess? Okay, as you can see here, partial v partial y. Okay, here is a cosine function x, right? And then so we can assume, okay, our phi is a function xy, and this is a fy is a function, and cosine 2 pi over lambda x minus ct. And this solution form can be guessed from what? Can be guessed from here. Okay, because our phi is a cosine and sine function. Okay, partial v partial y is a cosine and sine function. So I assume phi is also sine and cosine function. Okay, and here I can, okay, this you can assume sine function, it doesn't matter, but here we assume it's a cosine function. Okay, but times fy is a so-called amplitude later. Okay, so this is okay, one of the solution form to guess. So we're using the separation of variable again. Y and x will be separate into two functions, and by applying these two functions, we're using these two functions into our Gaussian equation. This is our Gaussian equation. Okay, partial square v partial square plus partial v partial y square should be equal to 0. By using this solution form, try to sub into this solution form and try to find out fy should look like. Okay, so this is after simplify, we have this. Okay, partial square f partial y squared minus 2 pi over lambda square f. This is equations can be, because the cosine and cosine will be, okay, cancel. So we have this function plus this function will be can be. So fy, this, okay, this function can be what? Written as, if you can solve this ODE here. So this ODE give us fy is okay, can be written as v1 is potential 2 pi over lambda y plus v2 is potential minus 2 pi over lambda y. Right? This is a typical ODE. Okay, ordinary differential equation with homogeneous. Okay, homogeneous ODE equation because this is equal to 0. And this is potential function. One is a positive sign, one is negative sign. And also this can be written as a hypercosine and hypersine function too, right? Okay, as you remember, okay, its potential, okay, can be written as a hypersine and hypercosine. So this is a constant C1 times hypersine function 2 pi y over lambda plus C2 hypercosine function 2 pi y over lambda. The set, okay, this is. So this is okay, fy should look like this. So our velocity potential is fy times cosine of this function, right? So our phi, okay, is our cosine 2 pi over lambda x minus ct times this phi, this times fy is here. This is fy, so this is fy here. So that's our velocity potential, okay, for this physical problem. And we only have two C1 and C2 constant have to determine it, right? Because we didn't apply any boundary condition yet. So by applying boundary condition, we can have C1 and C2 later. So, and then we know the velocity potential, we know the flow field. Okay? So for the boundary condition we have, on the bottom wall here, partial v partial y at y equal to minus h should be equal to 0. So that's no flow penetrate into the bottom wall, right? Okay? So v velocity at y equal to h should be equal to 0. So by applying the partial v partial y for this equation here and substitute y equal to minus h into this y here, you should be able to get this. Okay, C1 should be equal to C2 hypertangent 2 pi h over lambda. Okay, that's from this boundary condition we can, these two constants C1 and C2 is not independent, should be dependent each other. We know the C1, we know the other C2. We only have to know one, right? Because they have this relationship. So we can replace our C1 become C2 hypertangent 2 pi h. Okay, and this is another boundary condition. This boundary condition is what? On the free surface. Okay, as you can see, this is on the free surface here. So on the free surface here, we have a kinematic boundary condition. So by applying the kinematic boundary condition here, this is kinematic boundary condition, we can determine the C2. Okay, we can determine the C2. Okay. So C1 and C2 already determined, so we know this phi already. Okay, C2 is equal to this. So by C1 is C2 times hypertangent of this should be equal to C epsilon. Okay, so we have our Brazil potential already for this physical problem. Okay, and this Brazil potential can give us flow field at any point. Okay, for this